Hi, my name is Mike Holt, and I want to thank you for taking the time to watch this video about electric shock drownings. And really, this is going to be driven not by me, but it's going to be driven by Ed. Ed, if you could do me a favor, just introduce yourself and tell us about your passion, and then let's go to the program.
Certainly. My name is Ed Lethert. I'm from Minneapolis, Minnesota, and I am a member of the Electric Shock Drowning Prevention Association. And a lot of my activity now in the current time period is out promoting awareness of and means of mitigation of the electric shock drowning of people.
Well, my pleasure to be able to help participate and get your message out.
And it's my pleasure to be here, and I thank you for the opportunity.
You're welcome. All right, let's get into the program.
Electric shock drowning. It's interesting to note that if you ask the average person or make a comment to them about electric shock drowning or ESD, they look at you and say, what are you talking about? So what I see my task as is making people aware of a hazard that they are largely unaware of. I'd like to start out by showing you there are victims. And unfortunately, a majority of those victims in recent years have been children. And they have succumbed to electricity while in the water. And there are ways that this can be avoided. And we want to make sure that marinas, marine operators, and boaters and swimmers understand the hazards, much like you wouldn't play in the street in the traffic. So I'd also like to mention one particular case to show how tragic it can become. There was an incident here a couple of years ago where a family, a boating family, pulled into a marina. They plugged in a dog. Their dog fell off the back of the boat. The young son jumped in to try to help the dog. They're both in distress because of current in the water. The dad jumped in to help. Now he's in distress. The other son jumped in. Now he's in distress. And mom was ready to go in when somebody yelled, "Kill the power." Thankfully, the majority of them survived. Unfortunately, the one young son perished.
Do you know what was the cause of that?
That is in litigation, and so we don't have any information on that at this time.
Okay, we'll take a look at our slides again.
Okay. So where did this all start? Well, a gentleman by the name of James Schaefer, a marine surveyor from Florida, began to take note right around the turn of the century that there were AC currents in the water. And so Jim began to investigate this. And I can't give you all of the details, but I can tell you that he eventually connected up with another marine surveyor from Florida, and together they worked on a report, an investigation and report, which is referred to as the Coast Guard study, although actually it was a Coast Guard grant. And they visited a number of marinas, did extensive measuring to determine just what was going on and how serious the conditions were.
Well, Jim has actually been on our video team before in the past, so we're very familiar with him. And he's truly, like yourself, very gifted and very caring and very passionate.
Yeah.
Okay, let's go back to our little program.
Yeah, his colleague David Rifkin speaks very highly of him. I had the privilege of meeting Jim here last year. Unfortunately, Jim is not able to be active in this area anymore. So Jim and David basically put together this report, which in my opinion is the Bible on what's going on. In 2007, Jim wrote an article for the International Association of Electrical Inspectors magazine, and that came into my possession. And when I read that magazine, it triggered something inside of me, and I said, hey, I want to do something here. And so I've been active in this area ever since. Why don't we move into what is ESD, okay, or electric shock drowning? Actually, what it is, it's a unique form of drowning that's caused by the presence of AC currents in the water, okay? This occurs mainly in fresh water, lakes, rivers, and it can also occur in swimming pools, irrigation canals, ponds, or other similar places. The current can flow through the body of a living being. That can be a human being. It can even be an animal. And that can be bad in some cases. The current through the body can paralyze the skeletal muscles. I saw one doctor that was interviewed on this subject. He basically referred to it as cramps. So imagine if you're cramped up, you're in the water, you cannot keep yourself afloat, you're still breathing, you sink into the water, you ingest that water into your lungs, and you drown. So what happens is you wind up with a drowning that in many cases has wound up unexplained because the electric current wasn't enough to cause burns or provide any postmortem evidence that it had been involved. So research has determined that AC current of just 10 milliamps passing through the human body, and that's of an average adult individual, is sufficient to cause these muscular paralysis conditions, and it's considered the threshold for possible ESD incident. Now, for those who aren't familiar, that amount of current is the equivalent to 2% of the current that flows through a 60-watt, 120-volt light bulb. Alternating current through the body can paralyze the skeletal muscles, even at very low levels, as we just saw. If that current goes up a little higher, it can cause respiratory paralysis. In other words, your lungs cease to function. And that's just about as bad as the other method of perishing. If it goes higher, it can cause ventricular fibrillation. And extremely high currents typically associated with direct contact with something that's energized can cause full cardiac arrest. And animals are not immune, and so we've had a number of incidents where animals have gotten into the water and their owners have gone in to try to assist the animal, and it resulted in the owner or the individual, the human being, perishing. In some cases, the animal also perished. In other cases, the animal survived. But the bottom line is they went into the water without understanding what the problem was. And as a result, they became another victim. Okay, and by the way, there's a number of incidents where that has happened, where a human being has tried to help another human being, and they just wind up becoming an additional victim. Can't see. The victim of an electrically charged water may become partially or totally disabled, may or may not call for help, may or may not remain conscious, may or may not remain on the surface, and may make their situation worse if they are able to react by moving closer to the source of the problem rather than moving away from it. And that's a big concern with people in marinas, and also people like first responders who have to respond to these situations. People need to understand that you need to move away from the source of the current in order to have a chance to survive.
Well, think about it. If you're in the water and things are happening and your brain can't process the event that's taking place, you want to go where it's safe. Well, obviously, where it's safe is where the electric event is taking place.
Yes.
And so people don't recognize it. They don't know what's going on.
They don't know. And that's another interesting point, because in many cases, what is going to happen, you panic.
Yeah, of course.
And so you don't make rational decisions.
Exactly right.
So what causes this hazard to exist? Well, it takes two things. Typically. Now, when I say two things, this is pretty much the general case. There's always something else out there that we might not know about that can cause the problem. But generally speaking, the first thing is there must be some kind of an electrical fault in an electrical system that's in the water. And an electrical fault means that current that flows in this system has some way, through a defect or failure, found its way out of its normal channels and into the water. Okay? When that happens, current's going to flow. Okay, if the electrical system is intact and wired as it should be, then there are protections. The green wire that we are all familiar with provides a lot of that protection. But if that green wire is failing or failed or isn't there in the first place, then there's a chance that significant current will flow in the water because it's the only fault path available. And when that happens, then we see these situations where...
What kind of failures have you found where the effective ground fault current path, or as you call it, the green wire, what seems to have caused that? Any experiences you've seen?
It can be a broken conductor. It can be a disconnected conductor. I know of one case where, for reasons totally unknown, every ground wire on a 51-foot sailboat had been disconnected.
Really?
They were all hanging behind the panel. Wow. So sometimes it's people doing things they shouldn't do. They don't know what they're doing. Broken pins on short cord plugs or short cords that have been damaged because of chafing. Defective receptacles in marina pedestals, they're worn out and or the contacts are burned and burn off. So there could be a long list.
All right, let me explain this graphic here, if that's okay with you, Ed.
Sure, absolutely.
All right. This is representing the transformer, the power supply. And it could be the utility power supply coming in and then it goes over to a panel, or it could be there's a panels and then it comes over to a transformer that's at the dock. And then we have electrons. Let's just follow the circuit here. Electrons would leave the power supply, travel over, let's say, to some kind of source where you have a power outlet, whether it be a receptacle, and then it goes over from the shore and it goes to an inlet. Now this inlet is actually on the boat. So we take a cord, we plug it in here, it goes onto the boat, and then internal to the boat, you bring the hot wire and it goes over to the loads and it returns to the neutral, and then on the boat, neutral connects to the inlet, that connects to the cord, that connects to the receptacle, that connects back over to the source. So this is the source, so it leaves and it returns back here. Then we have what is called an effective ground fault current path, and a lot of times it's shown by a symbol ground, but it's really an effective ground fault current path, so that this connects the metal parts of the boat. And the metal parts of the boat, which is the AC ground bus, is required to be connected to the DC negative bus. And what standard requires this in a boat to do that, Ed?
The standard that requires this is the ABYC standard. That's the American Boat and Yacht Council. They basically are to boats what the NEC is to land-based electrical systems.
So from this shore power, now does this ABC standard cover shore power, the cord?
It does address the short cord.
Okay,
yes.
So you have a standard here in the boat, and the standard is, there's a cord standard. Inside the boat, you have the wiring. You connect the equipment grounding conductor or the effective ground fault current path to the DC bus, and then that connects to the motor, connects to the metal shaft, connects to the propeller, connects to anything metal like a rudder. So this is all the boat.
Yes.
And then that equipment grounding conductor or the effective ground fault current path goes from the boat to the inlet on the cord to the receptacle as a conductor or something conductive back over to the source.
Yes.
Now, you're showing a ground here. This ground connection here serves no purpose in clearing a fault. However, this ground might be here because of other reasons, maybe because you have a transformer out there.
And that's what that usually is the case, yes.
And so therefore, that's a requirement in the National Code that we make a connection to the ground, but this connection to the ground, showing the symbol here, serves no purpose in clearing a fault. So now we're going to go to the next graphic. This graphic's now taking the exact same thing, but it's just demonstrating what happens in the event of a fault. So we have current leaving the power supply, going into the shore power, going into the receptacle, onto the shore power cord, onto the inlet, in the boat. There's a fault to the case. fault current is always returning to the source. So it travels on this effective ground fault current path, back over to the inlet, on the cord, back to the receptacle, back over, and it goes back to the source. And this circuit shown here would cause the breaker at the short power outlet would trip almost immediately. At the same time, however, we got to keep in mind that the standard you described requires the AC ground bus to also be connected to the DC ground bus, and because of that, current will actually travel over to the motor, the engine, and then of course it'll be continuously coming out on all the metal parts, as well as going over to any of the metal parts that's in the water, and the electrons are traveling back. And the electrons, in this case here, there'll be smaller arrows because it's less current, simply because it's not as conductive a path. You're using water as a conductor, which is nowhere near as conductive as the effective ground fault current path. And in this case here, we'd have no problem clearing a fault.
Correct.
The next one shows, yeah, but what if your short power had a pin, you had it burnt out, the connection is lost, you lost the effective ground fault current path. That means that fault current would leave the source, and of course some current would be traveling on the load like the other example, but the current now is looking to get back to the source using this as the return path because of the fault here. Now it tries to go back on the short power cord at the inlet, but that's lost the effective ground fault current path. Since the AC ground bus is bonded or connected to the DC negative bus, then current would be traveling to the engine, and it would be traveling to the prop, and it would be traveling over to the rudders. Now, the only complaint I would give you for your graphic here is that you see these small arrows here of current?
Yeah.
That would be the exact same size arrows that direction.
Yeah.
Because the current won't change. So I don't want...
Yeah, right, I understand.
Yeah, I don't
what
want
you're
anybody
saying.
thinking that, well, now more current is going to travel this way because of that event, because it's a parallel. Now it becomes a series circuit. Before it was an individual series circuit. So, all I'm just saying is that, but the problem is that because you lost this, and we had, let me go back here, those size arrows are indicating that it is not enough fault current to open up the protection device in this device here. And that being the case, this will then stay continuously energized.
Right.
Now, right around all the metal parts that's in the water, there's going to be what is called a voltage gradient, because the electrons now they've been going in the water in a fault condition, but those electrons now, because it's an alternating current system, it's connected to the utility. The utility primary neutral is going to be multi-point grounded, and then the utility primary neutral is connected to the secondary neutral. The secondary neutral is connected to the service equipment. Your effective ground fault current path is connected to that, and that's how we clear a fault. But because you lost the effective ground fault current path, the current goes out to the boat. Everything that's metal in the water, it's going to be trying to get back over to the source. And because every building has a ground rod, and there's millions of ground rods, and all the poles, the electrons do this. It's like taking an eyedropper of ink and putting it in the water and then just squirting the eyedrop of ink. It does what? It just goes everywhere. But the greatest amount of, let's say, blue drop, the greatest amount you can see is concentrated right there. So we want to let it out in a way that we're not pushing it out, but it's right there. So you can see that would be your danger zone. Then it starts getting out. So your voltage gradient is greatest really, really close near the point. About, 6 to 15 feet is where, depending upon some factors of the weather. But then but what I'm saying is it disperses all over the place.
Yes.
Let's see the next graphic.
And keep in mind that if you're in a marina, every boat that's connected to shore power is a receptor of that current.
That is true, but let me respond to that. The fact that every other boat is a receptor, contrary to what people might think, because I've physically been in the water and I physically have tested this, the currents leaving, let's go back to this graphic here. The currents leaving this spot right here, going everywhere there is, if you look at that eyedropper, is that the intensity is here. Mm-hmm. The fact that you have other parts right here, yes, there's electrons going there, like they're going in the entire marina, like they're going everywhere in the planet. You will not get shocked by touching anything else at another point.
No. I agree. My point was you said ground rods everywhere, and all I'm saying is just like those ground rods are receiving that
Yes,
current.
you're 100%.
So
Yeah,
are all
you're
of
right.
the
Okay,
underwater
you're right. I
metals.
was saying, well, all on the ground has all the ground. Yeah,
Yeah.
but anything that's connected to the affected ground fault current path of anything that's
Yeah.
in the water or the earth is going to be another tractor.
Yes.
Now, that has nothing to do with anything that we're talking about in the sense that it means nothing other than electrons are going in there with the eyedropper, the intensity there, and it is going everywhere else. Right. But we won't get hurt anywhere else. But you will get hurt somewhere near that location.
Correct.
Perfect. Now, we talked about this, Ed, and you don't have control over this necessarily, is that this is represented where that eye drop of ink I described coming in the water. Jacob, do you understand what I'm saying? That represents that. The only thing is that probably I would take this square here, or this rectangle, and because here's the prop and the rudder, I would probably move it over a little bit here. Right, because it's it's that gradient that goes out from that location. So this is where the danger zone is. So now this current showing getting back over to the source here, okay? So let's just remind ourselves. It really is not like current going from there, going back to that point right there. It's going everywhere, every connection, everywhere, but every one of those electrons are returning to that supply. So they're just going to come in from a lot of different directions. And the fact that all those other paths, none of this matters over here. You're not going to get hurt. What matters is you're in the water, you're in that voltage gradient location. Let's follow this graphic here. Okay, current leaves the source, goes to the pedestal, comes over here. Oh, it's in the boat. We're in a boat right here, and there's a microwave. Somehow there's a fault to the equipment grounding conductor, so the current would then travel onto that equipment grounding conductor, which will get to the motor. Oh, we have a broken on the shore power. We have an open effective ground fault current path, and we're making a fault path here. Well, then the only path is like we've seen back over here, except we would have smaller arrows, right? The only path would be this voltage gradient here dispersed everywhere. So remember, it's like a sphere. It's going to be a circle. You know what I'm saying? And as you get closer, then it and if we could make colors, and if we could slice it, and you looked at it on a slice, you'd see like this, and then it would be red, and then it would be red for maybe like 10 or 12 feet, and then it gets yellow, because like, well, now then you get green. How big is that sphere is nobody knows. So then people are like, well, you know, we don't know. So now, I don't want to jump on here, but I just want to mention this if I could for you. And that is that it might not be a failure of a boat. It might be that you have a simple boat lift and you're running equipment and circuits out there, and then you're having this thing that's out of the water and nobody knows this, but this metal cable, this metal support connected to a metal piping that's being driven by an electric motor, and somehow the effective ground fault current path was open, but yet there was a failure. Now this becomes energized. And the sad thing, or the concern, is that when you drop this in the water, you get this great voltage gradient. You don't have enough current to trip the protection device. Yeah. Brian.
Yeah, I just, growing up in Southwest Florida, I spent a lot of time working on boat docks, and the number of very dangerous conditions that exist with boat docks are far beyond what anybody would expect as an electrician. Yeah, the boat dock's not working quite right. It still works. And they don't realize that as soon as they flip that switch to drop the boat dock, what actually is happening, it actually doesn't have a neutral connection. All the current is flowing on the equipment grounding conductor back because the neutral corroded off the terminal. And it's literally seconds, like one little mistake from creating a lethal condition. And I've seen them actually where the boat lift was energized, not in the water. I'm sure when it was in the water, it was energized as well. And if somebody had, which is common when you have a boat dock, like kids like to play in the water, if a kid had swum over to it and just grabbed onto this metal rail, they would have been electrocuted immediately.
Yep.
And up where I come from, unfortunately, in my opinion, the vast majority of boat lifts are powered by extension cords that run out the dock. And there's no weatherproofing of the connections. They simply plug things together like they would in the house. One extreme condition that I saw just a few weeks ago, the boat lift was plugged into an extension cord, which then dropped into the lake, laid on the lake bottom up to the shore, and then they buried it all the way up to where the receptacle was.
Okay, let's take a look at this slide. Ed, if you want to talk about this.
Sure. So ESD is often the result of a high impedance fault path where the current is not enough to trip the circuit breaker. In other words, the fault current is less than the rating of the circuit breaker. So if you're on a 30 amp circuit breaker and your fault current is only 5 amps, that breaker is not going to react. And what will happen then is you have an undetected fault that can continue on indefinitely until it gets bad enough to either trip the breaker or something else fails.
Well, there's no way it's going to trip the breaker.
No.
Because once it gets in the water, that fault return path will never improve.
Yeah.
And especially, I mean, you're not going to trip a 15 amp breaker, much less a 30 amp shore
right.
power circuit inside here.
Well, your entire boat lift energized in the water when we did some of our testing was under 9 amps.
Yeah.
So,
I mean, that
and
was the whole boat lift.
That was
connected
the
inside
entire
there,
boat lift.
You know.
Yeah.
All right, let's take a look at this one here. Talk about this one, Ed.
So just to give an example, there's also a lot of problems with people who don't know the rules for doing electrical work and doing their own work. This was a short cord that was had a new connector installed on it by the owner of a boat that wound up with a hot wire connected to the ground terminal on the connector.
Wow.
So when the boat was plugged in, the entire hull of the boat was now energized at 120 volts. This resulted in the death of both a mom and a child.
Yep, the daughter and the father. I think there was 3 people in the water, and the father is the one who made this connection.
Yes.
The father made the connection, kills his wife and his daughter
Yeah.
because he's thinking that, you know, that's a good idea.
Yeah.
All right, let's take a look at this one. All right, let me pick this up
Sure.
if I could. The next slide. Ground fault protection of marinas and docks. Now, we've talked about the fact that you have current going out, and if there's a fault, then the current goes into the water if there's no effect. If there was an effective ground fault current path, well, then the breaker trips. But if there's a failure, then it goes in the water, and Brian, we said 8 amps, 5 amps, depending upon the size of the mass of the material in the water, the conductivity of the water. I would say, well, no, I think we had like 1 or 2 amps when it was just a pole.
When it was just the pole, yeah, anywhere between a half an amp and 2 amps.
So depending upon the amount of area, because the electrons are leaving, right, the more it's surface area, then the greater paths, then you're going to have greater current. But you're never going to trip a protection device. So what the National Electrical Code requires in the 2020 code, okay, the National Electrical Code, let's talk about let's just say the National Electrical Code and the 2020 code. It requires that the circuit that goes out to the boat, that supplies the boat, and the circuit that goes to the boat be protected by a device called a ground fault protector. That is set at 30 milliamperes, which is 30 thousandths of an ampere. Now, the problem with having a device like that is that there's a lot of people who have boats that are a problem. So now when you put the ground fault protector out there, and this person had his boat for 20 years, and they come to a marina that's a new marina that's installed in the ground fault protectors. By the way, the code is not retroactive. So how many boat slips are there? How many shore power outlets are there in the year 2020 that's been around forever? So now the new boat lifts or the new docks are going to have this outlet. So this just a small amount. I've just been around the world. I didn't have a problem anywhere, and I'm coming into your new, brand new fancy thing, and you're telling me the problem is my boat. And so there's going to be a lot of pushback because these people don't want to believe it and they don't want to sit there and spend the money to make the connection and to make the correction. Brian?
Well, and I think what you mentioned earlier, and Ed both, that these are very low current faults. And so the reality of the matter is the boat could have had the problem for years. And it is legitimately a problem, but because it's very low current, it's never tripped a breaker before.
A lot of the problems are faults, particularly things like electric water heaters that have low level or high resistance faults in them. And another problem is a lot of miswiring that causes a neutral to ground bond. which will also trip the ground fault, and miswired inverters, where we have the situation, all these boats are dealing with objectionable current problems.
Well,
Objectionable current, for those who don't know, meaning current flowing on the ground wire as if it were part of the normal circuit path.
well, when GFCIs came out, people were complaining because now all this stuff doesn't work that always worked. Well, now you get rid of all the crap that didn't, that problem. Well, AFCIs, everybody's complaining about AFCIs because there was all kinds of miswiring inside the premises. Ground fault protection requirements come out in the code. People complaining about all that issue inside there. So let's take a look at this graphic here. So the protection that's required by the National Code in this 555.3 is based upon a 2017 reference. I'm not quite sure exactly what the reference is in the 2020 code.
555.35.
35.
35.
Okay, so they relocated the number in the 2020 code to the, but here is an example. This is set to protect at 30 milliamperes. Now, the 17 code has a 30 milliampere protection, and it's been revised since it was published. And in the 2020 code, it's going to require 30 milliampere protection for the individual feeder circuits that goes to the individual pedestals. But then the marina would have to have ground fault protection set at 100 milliamperes.
Actually, what it requires is 30 milliamps for the individual receptacle going to the boat.
Okay.
And it will allow up to 100
milliamperes for the
milliamps
feeder.
on the feeder that feeds the pedestal or pedestals.
And what's common, and you can correct me, Ed, as I've talked to people who's been involved in here, is that these pedestals often have almost like it's a dual pedestal. In other words, there's one side over here that you can pick up one boat slip, and there's another side you can pick up another boat slip.
Yeah, a typical pedestal will have either 2 or 4 receptacles.
Exactly. So now if you have two receptacles, meaning two different shore powers with a 30 and a 50, right?
Yes.
And a 30 and a 50, they run a 100 amp feeder to that pedestal. And if it had 4, then they run a 200 amp feeder. So let's just take 2. You have a 100 amp feeder, 3-gauge wire going to a single pedestal. 2020 code would require 100 milliampere protection for that circuit to the pedestal, 30 milliampere protection for the receptacles themselves for the shore power connection.
Correct.
And now we have a warning sign. So let's talk about this warning sign, Ed.
Okay, I put this in here because it is required by the 2017 NEC, and it's basically, the NEC says that all installations involving docks where electricity is used must have warning signs posted at all approaches, be visible at all approaches to that dock. And because they changed the 2017 code, now this even applies to private residential docks where it didn't before.
17 or the 20 code?
No, I believe it was it in 2002 that they exempted residential docks?
Oh, you're saying when they include it now in the 17
in
code?
2017,
I
they
didn't
added
realize that.
residential docks back in.
Wow. Wow,
And
to
so,
change our graphics.
And so
For new
the
installations.
code gives us some specific language, which we've had some discussions here. We felt the language fell a little short of what really was needed to do the job. So we've embellished a little the sign. We added no swimming so that people would understand why the warning is there. And then we also added some language at the bottom of the sign that lets people know that we're warning them that the conditions could be harmful or even lethal. Which brings us to the question that is often asked by people, especially families where you have children. When is it safe to go in the water? So if we could look at the next slide, the first thing I tell myself and then them is, let's not use the word safe, because safe implies there's no chance of anything going wrong. And that's just not the case. So
There is no such thing as a safe electrical installation
Right.
ever.
Right. And in fact, you go back to Article 90, what does it say? Practical safeguarding, not complete safeguarding, right? Anyway, so what we use, the folks at ESDPA, is we talk about risk. So we say if you want to reduce the risk to a low level or very low level, then the ESDPA has a recommendation that you not swim or enter the water, do anything in the water within 150 feet of electrical equipment or wiring. Okay. Now, some people think that's unreasonable. I believe if one were to look through the ESDPA's incident report, which you've published in your newsletter several times.
Every year. Right.
You'll see, yeah, and thank you for doing that. And I know David thanks you too, and all the board. Anyway, there are situations, even though they may be rare, where the distance is a big factor.
Well,
and
let me interrupt you there. Brian and I have been doing a lot of work, and we're doing all these calculations and all these meters and getting everything. And we come to the, you know what I think I'm going to do? I'm going to play a video that, what's that distance? Actually, I'm going to play two videos. I want to play one video showing me in the water. Okay. All right. We have the boat lift energized. How many amps is I carrying?
9.4.
9.4. The voltage gradient from this point right here, I've inched my way up this dock, getting over to that boat lift. At this point, 3 feet, I can feel the voltage. If I had been laying down, however, I would have been over there. You can move that way here. That would be about 9 volts. So if I had been swimming here, let me stop it for a quick second. In water, it takes about 6 volts for your body in water before your muscles get paralyzed. So if I had been laying down from that point that way, I can feel a tingle where I was sitting at that distance away, 3 feet away, because it's a matter of how wide that I put my feet. But if I had been in the water, I would have been okay in the water laying down up to where my foot was. But if it gets to be a 6 volt, no, it'd be 2 volts. It'd be 6 volts.
it's 2 volts per foot.
Right, 2 volts per foot. So, but I mean, at 6 feet, I would have been within, 6 volts.
You were approaching that.
I was approaching that, and then of course, then my brain I would know, who knows where I would swim to. I mean, let me get out of there. I would go inside
And
there.
you were pretty far away from that boat lift. I mean, you were at least 10 or 12 feet away from the boat
Yes,
lift.
we'll see that.
You could easily.
I was, my body, I get an electric shock drowning because my body would just crumble up. So I'm showing that 3 volts, I can sense it and I'm okay. But that 6 foot gradient, if we had to, we could put 1 voltmeter. This is actually a great demonstration. So even though the shock alert said, hey, you got voltage all the way out there, in reality, based upon the mass, okay, if we get to a smaller piece of metal, rather than the boat lift, that voltage gradient, I'm gonna hold this here so we know what the values are. Let's connect it to the pole over there and let's see what happens.
Okay.
We did the connection, but it's really irrelevant. It's just a smaller voltage gradient. So now let me show something up talking about safety as you were referencing. And this is after we spent days out there doing all kinds of things. Possibly. Okay, I'm doing a video having to do with electrical wiring and a boat dock. I've done a lot of different experiments. If you take a look at the post here, we got wires connected, tape here, and we got green wire going out there that represents the equipment grounding conductor, and a blue wire out there that's connected in there. We got all kinds of experiments, improving everything, figuring it all out. All right, let me make it real simple. You don't put any electric on a boat dock. That's how you make a boat dock safe. Now, if you're close to somebody else's boat dock, don't go into water. So if you have your own boat dock and you're not within 100 feet or 200 feet of somebody else, you're fine. You don't need electric on a boat dock. But if you're going to put electric on a boat dock, make sure all the circuits are GFCI protected. Now, we're not talking about a marina For sure, you don't go underwater in the marina. There's all kinds of issues there, and all kinds of requirements in Article 555 on how to do marina wiring. I was talking about an average person having a boat dock. If you get rid of your electric power to your boat dock, you got a boat lift, no problem. Put 24 volts, battery powered for your boat lift. If you're going to put electric receptacle out there, okay, fine. You want a charger, you want to hook up something in there, that's fine. Make sure it's GFCI protected. Lighting, make sure you have low voltage lighting. If you can put 120 volt lighting, make sure everything is plastic boxes, plastic races, plastic enclosures. You can buy switches that are all plastic. I can go here and I can go out there and I can energize that boat lift and I can show you, oh, look at this. The water's 120 volts, all this with the voltage gradient, all that. It doesn't matter. There's nothing you can do to be safe. This is my boat dock. I don't have anything electric on it. Now, I'm getting rid of the lift, so you can see it's all kind of mangled up there because I'm not using it right now. And when I did have it, it was 24 volt DC. I'm not sure what else I could tell you. So now let's go to your program.
Well, the last thing I would like to mention is, and I'm not sure, it sounds like Florida has at least one savvy electrician when it comes to dealing with docks. I look at the electrical profession the same way I would look, let's say, at the medical profession. You have physicians who are specialists, and the neurologist is not a cardiologist and vice versa. So what we need is electricians who are truly understanding of the requirements of installations around docks and water in general, that know what the special concerns are, particularly as it relates to Article 555, Article 682, Article 680 for swimming pools, and they need to have a good, solid understanding of what's going on and what needs to be done to make sure that the installations are fully compliant with the requirements of the NEC. I also, thank you. I wanted to mention that what we talked about today is applicable in a lot of areas, including swimming pools. And that applies to in-ground pools and above-ground pools. There was an incident in an above-ground pool where they had a light in the pool and somebody turned the switch on and there was current in the water. Decorative pools, fountains, aerators, and one of the new things we're seeing up in my area now is something called a thruster. They have names like Hydro Sweep and Weed Eater, and people buy these, they clamp them onto their dock, and they plug them in with an extension cord that lays on the dock. And then people unplug things, the extension cord falls in the water. They just have no concept of what is happening and the risks that they are creating. So again, we need to address these things.
I think, I'll be honest with you, I think you did an absolutely amazing job.
Well, thank you,
I
Dave.
mean, completely, absolutely amazing job. And I really appreciate you giving us the opportunity while we're here in the studio to make this video. And Brian, I'm sure you can get this thing burnt immediately. We're going to get this
for sure. We got to get this out.
Get this out, and we'll get a copy on the internet. And I mean, like right away. So, and we'll do all we can to promote this. And just want to tell you, thank you very much.
And thank you very, very much. It's been a pleasure being here.
God bless.